so I'm excited to announce introduce our first speaker of the semester. So Dr. Ning Zeng. He's a professor in the Department of Atmospheric and Ocean Science and the Earth Systems Science Interdisciplinary Center. Dr. Zeng got his undergrad in physics from the University of Science and Technology of China, and then got his MS in physics and his PhD in atmospheric science from the University of Arizona. He's worked at some pretty stellar and cool institutions like MIT, UCLA, the NASA Goddard Space Flight Center, Institute of Atmospheric Physics, and Max Planck Institute. Dr. Zeng's research is focused on climate change and carbon sequestration. He's a leading expert in carbon sequestration, particularly methods, specifically the wood vault method that we're going to hear about today in their presentation. So without further ado, I appreciate you coming to give our first seminar.
Thank you. It's a real pleasure to be first time at ENST to give a seminar, even though I've been around here for so long. My building is just 2 buildings up the street. And so over the years, I've known a relatively small number of faculty members in this department, from Bruce James to now Stephanie Lanson and so on. I actually have got quite some students from this department in my current class called How to Solve the Climate Change Problem. So over the years, of course, I've interacted with some other students from General Agricultural College. So I'm just gonna go ahead to say that removing carbon from atmosphere now, it has become essential because we have delayed our climate action. So the IPCC specifically has looked at the scenarios to reaching the Paris climate goal of, 2 degrees to 1.5 degrees. We need approximately reduce, to reach that goal, 1/3 of the effort will come from the current carbon sinks, other things. 1/3 of the effort will come from replace fossil fuel with renewable energy. But even with that aggressive scenario, we still cannot remove completely the fossil fuel emissions. We have hard to decarbonize sectors such as steelmaking, aviation, and so on, and methane emissions. And to those sense, it's going to be extremely difficult to cut them all. So we will need about approximately 1/3 of the effort will have to come from negative emissions. Specifically, this particular IPCC scenario, which is considered in middle of the road, calls for 10 gigatons CO2 per year negative emissions, now often called carbon dioxide removal. So the 2 terms are used interchangeably, but carbon dioxide removal has become more popular than negative emissions. 10 gigaton in 2050, and 20-some gigaton by 2100. That is huge because 10 gigaton is like almost 1/3 of the current fossil fuel emissions, just in 25 years. And this, of course, cannot happen overnight. You need to ramp it up over time. So the methods for removing CO2 can be broadly categorized into 2. One is so-called nature-based solutions. We all know planting trees is great. And however, this is very limited because it competes with other land use. And also the carbon sink saturates as forest matures. And so it's a great thing to do, but it cannot even remotely approach the scale that is needed given the current climate and emission situation. Now there's so much effort on engineering methods, like directly suck CO2 out of the atmosphere with chemical methods and put it underground, direct air capture. Yet there's another category that is now increasingly people are using the term hybrid solutions. That is, we do take advantage of nature's ability, for example, to do photosynthesis while capturing CO2. But we do need to do a little more than just planting trees or protect forests. So this is a type of things I'm going to focus on. I'll give 3 examples here. One is called ocean alkalinity enhancement. Ocean acidification is a problem, but ocean in the meantime is absorbing 1/4 of the fossil fuel emissions. And if we can add lime, for example, into the ocean, that will neutralize acidity, and the net effect is actually enhance ocean's ability to take up CO2. Another major category is called enhanced rock weathering. This also takes advantage of the natural process. That's how geological carbon cycle works, basically weathering of silicate rocks, which eventually leads to bicarbonate going into the ocean, then becomes carbonated rocks. We know limestones are all over the place. So, but natural geological process is very slow. So you can enhance it by, for example, spreading rock powder, the right type of silicated rock, like basalt rock, onto farms, and then that will increase the surface area dramatically. The volume and mass ratio, when particles are small, increases by the cube of diameter. So that will dramatically enhance the weathering process. So the net effect, again, is to remove CO2 from the atmosphere. So finally, this category called biomass burial now, that basically simply takes biomass that has no other use or sustainably managed forest and put it underground. This also mimics the natural process of coal formation. So this last category, biomass burial, is really what I'm going to talk about, is what I have been researching for more than a decade now. So the first paper, in fact, was published in 2008 called Carbon Sequestration via Wood Burial. To make a quick comment on the term carbon sequestration, I personally really like this term sequestration. And however, because it has been used for 20 or 30 years to now consider a less permanent sequestration method, so the community who works for longer term, like what's called a durable carbon removal now, talking about hundreds or thousands of years minimum as opposed to decades, now is using the term carbon dioxide removal. So I will say more carbon removal while here, see, I was still using sequestration, but I do like the term. I think it's actually pretty accurate. So initial reaction to that paper in 2008, you can find this comment from the journal's website. Is this a hoax for getting carbon credit? Brilliant or crazy? The idea of burying carbon in biomass makes sense. So that was actually a featured article in New Scientist. Your suggestion for sequestering carbon is a good one. The big question is how much would it really cost? In fact, now everything comes to the cost. Original paper on burying trees with great interest. That was actually our Tom Schelling. And then it might work. So that's Paul Crutzen. He was one guy who won Nobel Prize for his work, ozone hole. So he was, in fact, was very interested in the idea. He invited me to Max Planck Institute to give a seminar. But in most cases, is interesting. But let's talk about something else. So for all those years, so in recent few years, the idea started to got picked up. For example, probably one of the early ones that got this movement was the National Academy report on nets in 2019, where it simply stated it could be viable approaches to increasing carbon removal. The technology is simple and easily applied. Stop. Then nothing happened. Easily applied. And then in 2022, this paper did a in-depth analysis, compare wood burial with all the other methods that utilize biomass. And in particular, there's a lot of effort using biomass for energy, right? Cellulose, ethanol, and so on. So basically concluded that even though burial has no other benefits like getting energy out of it, it's really just all about carbon. But which means if you need a carbon price to make it work. So they calculated if the carbon price is above $125 per ton of CO2 equivalent, then this method is as good as any other methods, better in fact. So here's a short history of what has happened besides the initial paper. So in 2013, there was actually a DOE-supported workshop where we debated about this idea, actually wrote a paper talking about the potential, where it came to like 10 gigaton CO2 potential if you do this worldwide. And importantly, two projects, field projects happened. One was the Gemstone project, and then followed by the Montreal project, which I'll talk quite a bit about. And then in recent years, a number of organizations, both in terms, for example, the Yale Carbon Containment Lab, and then several companies started to work on this. And it also attracted different media coverage. For example, the Woodville team from University of Maryland, a student team, participating in Elon Musk's $100 million prize for carbon removal, was ranked 29 out of 1,000 some teams. But we did not get into top 15, where you would have got $1 million for phase one. But different things like MIT Technology Review, Forbes, and so on. More recently, we published a paper in Science talking about the durability of wood vaulting, and it was reported by Washington Post and 50 plus other media outlets. So the main idea of wood burial for carbon removal is really as simple as it sounds. Essentially, you dig a hole, you bury the wood down there. And the key, of course, is down where and under what condition you can actually preserve it so it does not decompose. So the engineering calls for a depth that is typically a few meters below the surface, importantly with clay soil, so that it can create a nosic, oxygen depleted condition. And this is very different from traditional soil carbon sequestration, because this wood is supposed to be below the active biosphere, not somewhere here. So of course, there are many experts really know what's going on here, in particular, I guess, in this zone. So this is an area that is actually, too deep for soil scientists and too shallow for geologists. So it's actually a lot of interesting scientific questions, answers I cannot find. But fundamentally, we need to keep it oxygen free so that most of the decomposers like fungi get killed. And this is, in fact, we know it will work because this is basically the first step of a coal formation process. Coal was formed in wetland situations typically, but slowly. It takes a long time, millions of years, before it gets to an environment that is conducive for coal formation. So most of the biomass, original biomass, is actually gone in, for example, peatland. I just came back from Indonesia, look at there. Just a small fraction of lignin-rich material form lignite and so on. So this is bioengineering approach, but you do it in one single shot. not 1 kilometer down, really just few meters down. But geologically, it would take thousands, maybe tens of thousands of years or longer to get to that kind of depths. So in practice, how does this going to look like? So here we envision a scenario, what we call a 1 wood vault unit on a 1 hectare of land, which is 100 by 100 meter, that is 2 soccer fields. And with 10 meter effective height, that much wood buried down there. That is 100,000 cubic meter of wood, which contains 0.1 megaton of CO2, just 2 soccer fields. And we estimate that you can get that much wood residual sustainably from 1 year of currently unexploited wood residuals from an area of 2,500 kilometers square, which is the size of Prince George's County plus Montgomery. So you may be thinking, oh, this starts to look like a landfill. In some sense, yes. Where am I? So in a 2022 paper, we proposed 7 versions of wood vaults. You can have it fully underground. You can have it fully above ground or halfway, half above, half below ground. Then you can do above ground shelter, or you can do super vault, like multiple, just stack them on top of each other. And then you can do it, what we call aquatic vault. You can dump them in the middle of a Nazic ocean, for example, the Black Sea, which is known to preserve ancient Greek ships and so on. And where oxygen level is low. You can put them in the desert where the conditions is dry, which can also preserve wood. Finally, there's a version called freeze vault. In this case, we can take it to Antarctica. In this case, you don't need to bury it. It's cold and dry. It's not going to decompose. Again, we actually have evidence right here. This shelter was built by Robert Scott on his way to compete, who was the first to get to the South Pole with Amundsen. This was his supply shelter. And it's still standing there practically intact. Canned food is still there. So, of course, this starts to sound like science fiction, is this really practical? So that comes to the 2 experiments we conducted over the years. So the first one was actually a gemstone project. 14 honor students from the gemstone program, advised by me and Bruce James. What they did was, for 2 years, they buried 125 discs, all coming out of the same loblolly pine, put them out, laid them out in a matrix, and then at 3 different depths, in addition to a surface disc. So over a 2-year period, they would take them out in groups and to see how the decomposition or the decay condition depends on the burial depths. So they concluded that even with pretty shallow burial, the deepest disc was buried at only 80 centimeters below the surface, just this much down. By the way, this was done at the Y Lab, thanks to, again, this college for supporting that. So what they found was, compared to the surface disc, which was left in the natural environment, the lifetime of the wood down at 80 centimeter can be extended from a few years to 60 years. Of course, many questions were unanswered by that, but that experiment really kind of established the first methodology for how to do wood burial for carbon sequestration. Then it came to a more realistic experiment, the Montreal project, where we collaborated with Quebec Agriculture Department did this wood burial in 2013. It was down at the corner of a crop field. There's a creek here, this is the crop field. So we dug a trench that is 20 meter by 8 meter and down to 5 meter. See, this was the engineering design. In particular, at the end of this long trench, we dug a smaller trench, a side trench, where we laid down a series of discs at predefined depths every half meter. So we could see how the depths plays an important role in the rate of decomposition. So the wood itself came from the waste wood collected along the creek, which they normally would collect and pile burn. That was done the season before and then piled on site. Then the actual operation was like this. You basically dig the hole. Here you see when the trench was complete, you see people standing there, you get a sense, 5 meter. It's pretty deep when you're actually down there looking up. And then you push the wood back into the trench, then you backfill the subsoil first and then the topsoil at the end, trying to minimize disturbance to the organic matter and so on. The whole operation took 4 hours and 35-ton wood was buried. Then 9 years later, we went back, we dug out down to the first 1.5 meters, and took out the first 3 pieces of the wooden discs we buried on the side trench. And this was the first 1.5 meter one, what it looked like when it came out. And so as you can see here, we are really going after the durability question. How long can it stay there? So here is the 3 photos. The one to the left was a photo of a disc before it was buried. And this was a disc that was left at the surface in 2013. So 9 years later, it looked like this. Somewhat miraculously, that little pile at the surface was still there. Then this was a log we dug out from 1.2 meter deep, buried 9 years later, where we cut it on site in half. You see the cross section. And in fact, the sawdust smelled like as fresh it was buried yesterday. So under the microscope, it looked like this. The surface one is pretty much all gone, even though it's still there, but you can see it's all gone, basically. But the one buried is totally intact, just look like a fresh piece of wood. Another interesting thing was, while the excavator was digging in 2013, at about 2 meter depths, where this arrow is pointing at, you see that hole right there? So the excavator poured out a log, threw it over. We rushed over to see it. We knew it's something exciting. And then the 3 ecologists I invited from McGill University immediately identified the log as red cedar. And that was later carbon-14 dated at 3,000 years old. So I remember standing there, we were looking at each other, I was thinking, do we really need to continue this experiment? So then, about 2 years ago, we finally got the equipment, the support, with collaborating with Professor Bing Hu from the engineering school. He's a super wood guy. He runs the super wood lab. And so we did all the kind of the measurement analysis on those wood, and from lignocellulose to FTIR, different things. Basically, we concluded this ancient wood, 3,000 years old, had a carbon loss no more than 5%, very conservatively, no more than 5%. So in fact, it looked like a piece of old furniture, the cross section. If you're interested, welcome to stop by my office one day. It's sitting there. And so importantly, we identified the key for preservation for so long with little loss is because of the low permeability clay soil at this site. So this site, Montreal, is part of the ancient Champlain Sea, which like Lake Champlain, Vermont, which was marine sediment, basically marine clay sediment, blue marl. And we actually measured the saturated hydraulic conductivity to be 2 times 10 to the minus 9 meter per second. So this gives us a very important data point. If you bury wood under this condition, and we know it's going to be preserved for 3,000 years or longer, right? So it's so important such that the reviewers of science actually liked it. So now come back to the basic of biology, asking the question, really theoretically, what can make wood preserve for thousands of years or longer? So there are 3, this is actually well known because decomposers need oxygen, water, and suitable temperature to survive. So if we can cut off any of these 3, any, doesn't have to be all 3, any one of them to make it bone dry or freezing cold or oxygen free, then we can preserve wood for a long, long time. So we have been focused on anazic condition, mostly because we think this seems to be more widely applicable with more practical to actually achieve. So the 2 things you can do is one is sealing well, like with clay. One is waterlogging, which also helps. That is also partly the case in Montreal, the Montreal wood. Now, as I said earlier, the operation sounds like a kind of landfill. Many people, in fact, they just think it's landfill, but it's actually not. So landfill is partially anaerobic, not totally anaerobic. Maybe at the bottom of a long-lasting landfill, a deep landfill, it could become more or less anaerobic. But a wood vault wants to be totally oxygen-free, 0 oxygen, not 1% oxygen. Okay. Oceanographers call like 2 to 5% oxygen condition anazic, but that's not good enough for thousands of years or longer. At least when we initially go do this conservatively. And it's clean wood, there's no trash, and it's cold, not like a bioreactor in a landfill. And methane generation, we think it's negligible. And it stabilizes after weeks to months. And has no leachate whatsoever that would damage the environment, which unfortunately, this is not recognized by regulators right now. So now, I said, we did a 9-year experiment. So you would be wondering, no matter how well it's preserved after 9 years, how do you extrapolate that to 1,000 years? Any experiment error bar there, by the time you extrapolate to 1,000 years, can lead you to go in the other direction, right? So, and fortunately, we have a lot of geological and archaeological evidence to support the possibility of preserving wood for a long, long time. So without going into all the details, and from hundreds of years to millions of years. Like the very last one was in Umbria, central Italy. And when they were, in fact, mining clay and found this forest buried there. And I actually happened to have visited this site before I had this idea and collected a piece. And it was really well preserved. It doesn't look like, it looks kind of not so great, but it's actually really well preserved. And only the stumps. So now what can we do? So we have estimated, we had published a paper and most recent work as well, and to look at wood sourcing. So ultimately the method, I have been talking about durability. So the other major question is really, where do you get your wood source sustainably? So there are 2 types of wood source. One is residuals. for example, in our area, we have a lot of urban waste wood. How many of you have heard about the waste wood at Camp Small, Baltimore got burned? Right? So we actually have a lot, and the DC metro area is having a major waste wood problem, in fact. So we have estimated globally, there's 1 to 2 gigaton CO2 potential. So in this case, the baseline is very simple. If you leave it there as mulch, and it just decays after a few years. If we can use a wood burial project to preserve it, then it's just this difference. That's the carbon you actually sequester. So give an example which was done in 2023 by Carbon Lockdown, which is a startup spun out of my research I co-founded. So it was considered the world's first commercial scale wood vault project. So the wood came from Camp Small, Baltimore. So this site has accumulated 35,000 tons of wood they can't get rid of. In fact, before we approached them, they just had to have an emergency contract. They paid $90 a ton to a mulch facility to take it away. So they were very happy we offered to take it away for free. And then the process is pretty much similar to Montreal. It's really, digging a hole, except this, of course, it's bigger this time. And the logs were laid down very carefully to maximize the space use efficiency. And at the end, the soil is pushed back and compacted. And finally, the surface is backfilled with the topsoil and then seeded with pollinator species. So, half a year later, 24 was just growing nicely. The surface will regrade it a little bit, so essentially you can barely see it. What else do I want to say? So this one buried 100 tons of wood, and the construction took 1 day. Carbon efficiency, meaning how much of the original carbon is actually used for carbon removal, greater than 90%. Well, another important number is the fossil fuel emissions associated with machine operation. Most importantly, to transport wood from Baltimore to Cecil County, 50-mile one way, added together to 5% of the carbon sequester. And so there are many opportunities right now we can take advantage of in terms of using wood residual. For example, a major problem is a fire in the West, which has lately come to the East. And there are a number of studies now showing, for example, the Forest Service has estimated that they will need to thin about 1 gigaton in the next 10 years, just national forests only, a gigaton. And then we have, for example, Hurricane Helene damaged a lot of trees. We actually working with a couple of groups trying to utilize that. Then urban waste wood I just mentioned. So here is not about wood source, but it's about burial site. We have a lot of abandoned mines, including Maryland and quarries and so on. So the hole is already there, and they actually need to be rehabilitated. So if we can fill the wood first before we top it with soil, this would have a lot of co-benefits and also makes the operation a lot cheaper. So of course, if we want to get a 10 gigaton scale with this method, imagine, we will have to manage the forests. So in this case, the baseline is a little more complicated. If you start from, let's say, restoring the deforested Amazon rainforest, you start from 0 carbon, you grow. If you leave the forest alone, it basically, as I said earlier, levels off after a few decades. There might be a small increase before major disturbance kicks in, but in general, the vigorous growth is in earlier decades. So around somewhere this time, you can probably start to do some harvesting And the initial harvest will generate disturbance, you actually lose something unless you utilize all the tiny little biomass, which is probably not a great idea anyway. So we're already talking about these larger pieces. So you lose some, but because the carbon is stored there, if you add the two things up, so they quickly catch up, and then you would just increase indefinitely. So essentially, we're talking about it's a major change the way you do it from just preserving forests. So we actually estimate the potential of this method if you would do manage a forest worldwide. And in doing this analysis, we used a global carbon cycle model called Vegas, which we use in our Earth system coupled climate carbon cycle model. The model itself has been used 3 times in the IPCC report. So we considered this constraint, current land use, conservation, we assume the 50% don't touch, 50% tropical rainforest, 20% and boreal forest, and then steep slopes will be very difficult, expensive, erosion and so on. So don't touch it. And we also have other wood use. So after we subtract all those, we end up with a global total of 10 gigatons CO2. Coincidentally, that's what IPCC said we need negative emissions by 2050. You look at the spatial distribution, let's say simply compare it with these different regions' current fossil fuel emissions. So US and China are similar, about 10%, which is very significant. The current US carbon sink, natural carbon sink because of regrowth and so on, and is just about this number. But now we can do it sustainably if you continue this. Then the boreal regions, like about 50%. And then the big elephant is in the tropics. So, of course, there are different concerns when you do something like this, some engineering at this scale. First, durability is project dependent, highly local. You cannot have the best soil everywhere. If you transport things long distance enough, it becomes too expensive, burns too much fossil fuel. So it's a local thing. This is very different from making machines and copy them a million times. So you have to do it in consideration local condition. Another major one is nutrient lockup. Unfortunately, we are locking up wood only. That's another reason besides, I said, like it's space efficiency and so on. And nutrient lockup, fortunately, wood is nutrient poor. So it's 20-1 for leaves, but for wood, carbon nitrogen ratio is 200-1. So it's very small, in fact, compared to, for example, the natural nitrogen deposition. Globally speaking, it's 10% of it. But again, it's a local issue. So we know, of course, you guys know our plantation in Southeast, they actually do fertilize sometimes. So if it comes to it, we have to make the decision, do we want to fertilize it, or we just reduce the intensity of doing any operation like this. So I'll leave others here, including unintended consequences. We're talking about, if you go to actually 10 gigaton, we're talking about extremely large scale. So it's definitely many, many things to worry to make sure it's done right. I'm not, saying this number very lightly, even though on paper, the model just comes out with a number. Let's not move forward now. Okay, so I have a couple more slides. Finally, I want to take a look from a carbon cycle point of view. I made the comment, this is very important from forest protection or planting trees. So, and then why we can get to this scale. This sounds like stunning, 10 gigaton. Turns out that's, again, thanks to photosynthesis. The terrestrial biosphere each year takes up 220 gigaton CO2, which is 6 times current fossil fuel emissions. This is what we call the net primary productivity. And of course, in the natural carbon cycle, everything's in balance. So pretty much all of that 220 goes back into the atmosphere as leaves fall and trees die. So the net is practically zero. There is currently actually a slight imbalance, which is what we call the missing carbon sink. So now the wood barrier idea is we take that part that would otherwise decompose, just a small fraction, 5% of that would give us 10 gigaton. If we can put it away permanently, so it will be a carbon sequestration, carbon storage. In fact, if you can imagine, how about if after the climate crisis is over, who knows how many generations later, that wood will still be there. It's actually pretty easily accessible. So it can be a bioenergy, biomass reserve. In fact, eventually we will run out of easily accessible fossil fuel. And this actually creates a new energy and biomass reserve. In my mind, you guys probably believe this more than I do. In the future, everything, all the material has to be made from this sustainably generated like biomaterial. So another thing is this natural cycle just keeps going. As I say, like the Camp Small wood just got burned if you don't do anything about it. So if we don't do it, the opportunity is lost. If we do it too much, it's not sustainable. If we don't do it, we lose the opportunity. So but basically what we are doing is we are growing chicken, not just for the chicken, but for the eggs. Growing chicken for the chicken is reforestation for carbon sequestration. Growing chicken for the egg is wood burial. So if we want to even talk about a little more big picture, look at the Earth system as a whole. And this kind of reversible biomass storage and current carbon sequestration actually can be used as a tool to manage our Earth system. We can't go back to agricultural time. We are in an industrial time. And so realistically, we will have to manage the Earth as opposed to go back to 10,000 years ago, an early agricultural idealized situation. So if you look at this atmosphere CO2 concentration time series, starting from the last glacial maxima here, as CO2 increase over deglaciation, and then at the Holocene maximum somewhere here, the climate theory called Milankovitch theory actually says we would go into the next ice age. In fact, if there is no human, very likely the northern part of Canada would already be covered permanently by ice now. This is based on the best analog we have from, let's go to mid-19 deglaciation 700,000 years ago. And this did not happen because of two main reasons. One is the advent of agriculture, where we slash and burn and actually release CO2 and methane to increase CO2. And that is what's called the early Anthropocene hypothesis. And then, of course, the big thing is the Industrial Revolution, which really shot up the CO2 in a much shorter amount of time. So now many scientists believe, like Jim Hansen says, we need to bring CO2 down to 350. Others say we actually simply just need to go back to 280 for industrial time. Whatever it is, we know that 560 double CO2 is not acceptable. Even 420 now is not acceptable. So we need to draw down. So if we use buried wood as a thermostat, we can now bury carbon at a rate of 10 gigaton per year. So we can draw down pretty much a big chunk of this carbon we need to draw down according to the best understanding we have on the time scale of 100 years. So 10 gigaton a year for 100 years, that's what, 1,000 gigaton, which basically is that's how much we have emitted so far. And if, let's say, 1,000, 3,000 years later we are here, we actually need to burn some CO2, we can actually dig it out and burn it or use it relatively quickly on the timescale of decades. So that's kind of, like somewhat a grandiose view of this idea. So finally, my conclusion. So wood barrier is the first step of the fossilization process. It's a natural way to undo fossil fuel burning. And a key question, durability, we think if you do it right, you can get thousands of years or longer. And it's distributed, highly scalable, and low cost. We actually estimate the cost to be $10 to $50 per ton if optimized. Right now, it's more expensive than that. And it's relatively easy to monitor and verify. The wood is just there. You can just dig it out if you don't believe it, see if it's still there or not, right? The land occupied by wood body is small, the footprint relative to the amount of carbon buried. And there will be environmental impact to some degree, but we think compared to many other methods, other options, this can be kept at minimum. If you do it in the right way, there are many co-benefits: manage waste of wood, fire risk reduction, mine remediation, and the surface can be reused in most cases for you can still grow crops on it. And sustainable wood sourcing is critical. Provides green jobs and locally around the world, and in fact, mostly in the tropics, that's the potential there. And we think it's economically viable for large-scale importation now, as long as you are willing to pay some dollars for a ton of carbon. So that's, I think, everything I have. So this QR code gets you to my homepage, but you can Google my name very easily. Thank you.
I think we have time for a question or two.
Very much enjoyed your presentation. I'm wondering, you've probably done sort of back of the envelope calculations about what's the sort of viable transport distance that you could, how far can you transport these wood materials and still bury them and make it a viable option? Yeah,
in fact, that's in this particular Potomac project example, 50-mile one way. We used what's called roll-off truck. So it's not the giant Logan truck. It's not the most efficient. Each one carried 10 ton. That's like 3/4 of the emissions comes from that transport. And then the other 1/4 is from excavation and burial. So that adds to 5% of the buried carbon. So if you double the distance, you can get to close to maybe 10%, 8%. So theoretically, you would say, even if the emission is 50% of the buried carbon, that seems it's still carbon positive, whatever the positive means here, right? But personally, my feeling is I would not want to get above 10%. The efficiency I would want to be above 90%.
So 100
Like 100 mile would be, what I would consider. I would hesitate to go beyond 100 mile. And however, DNV actually did a life cycle analysis for our Potomac project. So they did what's called a sensitivity LCA analysis. They added reel and shipping options. Turned out, if you find a reel station very close by, you can load it onto a reel. For example, like we are moving so much coal from Wyoming to the East Coast, right? But those carts go back empty. If you put them there, bury them in the Wyoming mines, that seems work out as well. So trucking, so I should limit that distance with trucking. Above 100-mile trucking becomes a little bit challenging.
What do you think needs to happen in order for this to become more like widely implemented as a practice?
First, it's already happening. I can count 10 to 20, possibly more companies are actually working on this. Everybody's just starting, including carbon lockdown. So far, but there are a number of challenges. For example, there are 2 or 3 companies possibly got venture investment money, right? You pay me $150 per ton, I can do a reasonable project right now. So money is one thing, but it's moving now, right? But there are some other obstacles that I totally did not expect. And in fact, in Maryland, I have been pushing. So we did this 100-ton trial, thanks to the support of a Swedish company. You know, they want to do their carbon net zero, you know, that sort of thing. That's actually like the main support right now. Just there are a few good guys, rich guys who want to support different novel methods. This is still considered very novel in the carbon removal community. And one obstacle we have run into, most other companies in the US and Canada as well, is permitting. So wood vault does not exist in anybody's framework. So like Maryland Department of Environment considers this a landfill. They said the only way we can approve it is landfill. And so like the pilot project we did, the KLB farm in Cecil County, where Stephanie Lanson did the biodigester study. That's the agriculture easement land, which does not allow landfill. So we got stuck there. Then we found another site in Charles County, Southern Maryland. And then after back and forth, then Charles County said, we actually don't allow landfill on private land at all. So, and then there is actually a legislative effort at the Maryland General Assembly introduced by Delegate Mary Lehman of College Park and Senator Jason Gallion of Cecil County. So a bipartisan bill tried to basically define wood vault as a climate positive technology should not be, should be a different category. Basically says, allow the university to do some research projects. But that did not go through. Did not even get to the voting, the hearing stage. I was scheduled to be at the hearing, but it was called off because of the strong objection from NDE. So I had trouble to get them to understand. When I asked them, what is your concern about wood vault? They said fire. We've seen, like buried wood burning or landfill wood burning. I'm like, well, wood vault by definition has no oxygen. It does not burn. There are 2 international standards actually set for biomass burial now. And an academic protocol, which is more strict, written by myself and a couple other faculties, other universities. So that is actually currently right now something that I've been really struggling over almost 2 years now. So, but there are many other challenges as well, I think. But we really need to get something going. Sorry, was there a hand earlier somewhere?
Yeah, earlier I was actually gonna ask, I assume if rail is more efficient for this, shipping is as well. Have you guys looked at like any novel combinations? Like a lot of ships get sunk for artificial reefs. Have you looked at just shoving a hull full of wood and sink it in Lake Superior as a way of doing a wood vault, or?
Yeah, that will be the way. In fact, one of the examples I had earlier was actually the sunken wood lumber
I was wondering like.
at the bottom,
Yeah.
at the bottom of the Lake in Michigan here, at least 100 years old. So that comes to the durability issue. So for example, last year, they actually found at the bottom of Southern Ocean near Antarctica, the Ernest Shackleton's sunken ship, right? Almost perfectly well preserved. So that's not even totally anosmic, but it's very cold. But when you look at the photo carefully, you see like urchins and different things are working on it. So 100 years, no problem. And being a climate scientist, I actually think we need at least 100 years because the natural process will take thousands of years or longer. The longest, carbonate cycle would take hundreds of thousands of years to take enough carbon. Even though durability of 100 is considered high now, but I personally feel like living in like this kind of condition is still a little bit concerning. But if you have wasted wood thrown in there, it's better than, I think, have it, go into a landfill.
So like if you're already disposing of a steel-hulled ship and you fill it with wood, like that would be viable, right?
Yeah,
It's
yeah.
kind of like an extra container.
Yeah, if the economics of that, so the wood is really no other good use, and this can be done relatively cheaply locally, even though the durability is not as strong, potentially not as strong, but it's still, still doable, I would say. So we need to analyze these different factors together, put up like a matrix or something.
Cool.
We gotta exit the room at 4 o'clock so we can chat out in the hall or head over to this hall or the other hall. And we'll have to